Okay, so we're in chapter 5 and we're talking about section 5, direct measurements. And so we're going to use common technical measuring instruments. And one thing we talk about is a digital display. The simplest kind of measuring device to use is one in which the output is a digital display. For example, in a digital clock or digital voltmeter, the measured quantity is translated into electrical signals and each digit of the measurement number is displayed. A digital display is easy to read, but most technical work involves direct measurement, where the numerical reading is displayed on some sort of scale. Reading the scale correctly requires skill and the ability to estimate accurately between scale divisions. When we talk about length measurements, it involves many different instruments that produce either fractions or decimal number readouts. Carpenters, electricians, plumbers, roofers, and machinists all use rulers, yardsticks, or other devices to make length measurements. Each instrument is made with a different scale that determines the precision of the measurement that can be made. The more precise the measurement has to be, the smaller the scale divisions need to be. Okay, so if you can look here at the top, we've got 1, 2, 3, 4, 5, 6, 7, 8 divisions. And at the bottom on this 1 inch, they've even divided those into, now we have 16. So this would get you to 1/8. This is going to get you to 1/16 down here. A carpenter or roofer may need to measure no closer than 1/8 or 1/16, but a machinist will often need a scale graduated to 30/2 or 64ths of an inch. The finely engraved steel rule shown is a machinist rule. So on this, they've even got it down to the 30/2 and 64ths of an inch, and here's their 1 inch mark. So some machinist rules are marked in tenths or hundredths of an inch on one side and may be marked in metric units on the other side, because they've got to be able to get things that are very, very precise. So notice that on all these rules, only a few scale markings are actually labeled with the numbers. It would be easy to read a scale marked like this if all of the markings were there. But this, if you'll look at this, that's a lot longer than an inch, and there's not enough room to mark. If we moved to where an inch would actually be, about right here, there wouldn't be enough room to put all those numbers. So that's why they have to only label a couple of them, and you have to figure out what the other ones are. So there are 4 spaces in the first 1 interval. The smallest division is therefore 1/4 of an inch. So 1, 2, 3, 4. So 1/4, and they've got this label down here, 1/4. This would be 2/4, which is the same as 1/2, 3/4, and then 4/4 would give you 1. 4/4 would be the same as 1. To use the rule, once you have mentally labeled all scale markings, first count the inches, then count the number of smallest divisions from the last whole inch mark. So if you start counting here, we would go past the 1, 1, 2, 3, 4, 5, 6, 7, to the next one, which would be 8. So this ruler is going up by 8s. If the length of the object being measured falls between scale divisions, record the nearest scale division. In this measurement, if you'll look closely, there's actually 16 lines before you get to the 1. So this is going up by 1/16. Each one of these lines would be a 16th. When we consider using micrometers, a steel rule can be used to measure lengths of plus or minus 1/32 of an inch, plus or minus 1/64 of an inch, or as fine as plus or minus 1/100th of an inch. To measure lengths with greater accuracy than this, more specialized instruments are needed. A micrometer can be used to measure lengths of plus or minus 0.001 of an inch, 1/1000th of an inch. It's just really, really, really tiny. So a modern digital micrometer is accurate to point to 1. This is our tenths place, remember, hundredths, thousandths. This would be 10,000ths place. and the measurement is given as a digital readout in inches or millimeters. To record scale, our two scales are measured on a micrometer. The first scale, marked on the sleeve, records the movement of a screw machined accurately to 40 threads per inch. The smallest divisions on the scale record movements of the spindle to 1/40th of an inch, or 0.025 or 25,000th. The second scale is marked on the rotating spindle. One complete turn on the thimble advances the screw one turn, or 1/40th of an inch. The thimble scale has 25 divisions, so that each mark on the thimble scale represents a spindle movement of 1/25th times 1/40th, which is 1/1000th of an inch. To read a micrometer, we want to follow these steps. First, you want to read the largest number visible on the sleeve and multiply this number by 0.100 or 1/10. So they've got that they want to read the 4. So they're going to take the 4 and multiply it by 4/10 and get 0.400 inches. Then it says to read the number of additional scale spaces visible on the sleeve. This will be 0, 1, 2, or 3. So we have 3 additional spaces that are visible. So if you look past the 4, you can see that there's 1, 2, 3 other marks. So you're going to take that 3 and multiply it by 0.025 to get 0.075. To read a micrometer, the step 3 that you're going to need to use is read the number in the thimble scale opposite the horizontal line on the sleeve and multiply that number by 0.001. So we've got 10 here, 15 here, so 11, 12, 13. 13 times 0.001 is going to get you 0.013. Now you're going to take all of the numbers that you came up with and add them together for your final answer of 488 thousandths inches. So here's another example. First thing we're going to do is we're going to read the first number that we come to, which is 2. We're going to multiply that by 0.1 or 1/10, which is 0.200 inches. Then we're going to look at how many spaces can we read past the 2. So it looks like we got 1 line, 2 lines, 3 lines. So they did 3 times 0.2025 and they got 75 thousandths. Then the thimble part, we've got 15, 16, 17, 18, 15, 16, 17, 18, 19. And so they did 19 times 1,000th, which got them 19 thousandths. They added the numbers together to get 0.294. Okay, here's another example if you want to check it out. Metric micrometers are easy to read. Each small division on the sleeve represents 0.5 millimeters, or 5/10 of a millimeter. The thimble scale is divided into 50 spaces, therefore each division, 1/50th times 0.5 millimeters, is 1/100th of a millimeter, or 0.01 millimeters. So turning the thimble scale of the metric micrometers, one scale division advances the spindle 1/100th of a millimeter, or 0.001. To read a metric micrometer, you're going to follow these steps. Read the largest mark visible on the sleeve. So I'm seeing a 5 and multiply that number. I'm sorry. So we want to count 5, 6, 7, 8. And so 8 would be the largest number times 1 millimeter. So they got 8 millimeters. Then read the number of additional half spaces visible on the sleeve. So now we're going to look at the bottom. So past 8, it looks like there's 1 half space because 1, 2, 3, that got us 8, and it looks like we can barely see one more. We're going to multiply this number by 0.5 millimeters. Then we want to read the number on the thimble scale opposite the horizontal line on the sleeve and multiply this number by 1 millimeter. So they're talking about these numbers right here. So we've got 35, 36, 37. 37 times 0.01 is going to be 37/100th. Then they add those up to get the number of total millimeters. So here we have an example. We've got 15, 16, 17, so 17 times 1 millimeter. If you look past 17, I'm seeing barely one line here, so times 0.5 millimeters. And then we've got 20 and 21 on the big thimble, which is going to get us 0.21 millimeters, and then you add those together to get your total sum. When more accurate length measurements are needed, the vernier micrometer can be used to measure an accuracy of plus or minus 1/10,000th of an inch. So that's getting even closer, even more specific. So the 10 vernier marks cover a distance equal to 9 thimble scale divisions as shown on the spread. To read the vernier micrometer, follow the largest 3 steps given for the ordinary micrometer. Then find the number on the line of the vernier that lines up exactly with any line on the thimble scale. Multiply this number by 0.001 and add it to our other 3 distances. So it looks like they would pick, it would be closest to this 10 here. And so that's what they would need. So 9 thimble spaces takes up this much room. And so it looks like it's the closest to this top one. Okay, and so they've got on the vernier scale on this one that this was this number and it went 1, 2, it was pointing at 3, so they multiplied that by the thousandths, then they added it to the rest of the numbers that we had before using the other drawing. So we've got another instrument that we're going to use here, and here's an example of the one that is the physical one that you're going to have to move, and then you've got a digital machine. Notice that on the manual instrument, each inch of the main scale is divided into 40 parts, so that each of the smallest divisions on the scale is 0.025. Every 4th division or 10th of an inch is numbered. The numbered mark represents 0.1, 0.2, 0.3, and so on and so forth. The sliding one is divided into 25 equal parts by 5 seconds. These 25 divisions on the vernier scale cover the same length as 24 divisions on the main scale. So they've got an example of that drawn down here. To read this, you want to read the number on the whole inch division on the main scale to the left of the vernier 0. So they've got 3 inches here, and that's representing this 3 inch. Then you want to read the numbers of tenths of the main scale to the left of the vernier 0. Multiply that number by 0.1. So we've got 1, 2, 3, 4, 5, 6, 7, 8 tenths. And so that's where they're getting the 8 tenths. Okay. Next, you want to read the number of additional whole spaces on the main scale to the left of the 0. Multiply this number by 0.025. So they went to the 8. They've got 1, 2, 3 spaces past that. They multiplied that by 0.25. And then on the sliding scale, find the number of the line that lines up exactly with any line on the main scale. So they're saying that 15, because 15 lines up exactly with this on the main scale. The rest of them are off. So they multiplied by 15 times 0.001. Then they added all of those numbers up to get the final answer. Here's another example of that. So we've got 2 inches, then we've got 2 tenths, then we went over 2 spaces to get 2 times 0.025, and then last, the 15 is the number that lines up perfectly with the number on the other scale, and so they multiplied that by 0.001 and added all those together. You talk about a protractor. It's used to draw and measure angles. The simplest kind of protractor is shown here. It's graduated in degrees with every 10th degree labeled with a number. In measuring or drawing angles with a protractor, be certain that the vertex of the angle is exactly at the center of the protractor base, and one side of the angle should be placed along the 0 to 100. So if this is the angle that I'm trying to measure, I want to make sure that my center of my angle is lined up right in the middle, and that one side of the angle is lined up at the base. Now, notice that you also have, this goes from 0 to 180 this way, and this goes from 0 to 180 this way. Well, I know that the 90-degree angle is right here. Okay, so this makes a 90-degree angle. So one thing I know immediately is that because this angle has to be smaller than 90 degrees, I can't call it 130. I'm going to have to use the number on the bottom, which is 50 degrees. So this angle is 50 degrees. Now, if I were to measure the other angle that's not colored blue, right, so if I'm talking about this angle right here, that one would be the one that's 150 degrees. The bevel protractor is very useful in shop work because it can be adjusted with an accuracy of plus or minus 5 degrees, or 0.5, 5/10 of a degree. The angle being measured is read directly from the movable scale. Okay, so for very accurate angle measurements, the vernier protractor can be used with an accuracy of plus or minus 1/60th of a degree, or 1 minute, because 60 minutes equals a degree. So they've got where this is 42 degrees, and then on the bottom we even have a more precise scale. To read this kind of scale, you want to read the number of whole degrees on the main scale between the 0 on the main scale and the 0 on the vernier scale. Okay, and then you want to find the vernier scale line up on the left of the vernier 0 that lines up exactly with the main scale reading mark. So they started with our 42, and then they said the 45 is the number that lines up exactly. If you look at this 45, it is lined up exactly with the 60. So they've got 42 degrees and 45 seconds. I'm sorry, the first line is a minute, and if it had 2 lines after it, it would be a second. So 42 degrees and 45 minutes. Many measuring instruments convert the measurement into electrical signal and then display the signal by means of a pointer and a decimal scale. Instruments of this kind are called meters. Are used to measure electrical quantities such as voltage, current, or power, and other quantities such as air pressure, flow rates, or speed. As with length scales, not every division on the meter scale is labeled, and practice is required in order to read meters quickly and correctly. The range of a meter is a full scale of maximum reading. The main divisions of the scale are numbered in divisions. The small divisions are the smallest marked portions of the main division. On a uniform scale, all marks are equally spaced, and all divisions represent the same quantity. So the following voltmeter has a uniform scale. The range is 10 volts because that's all we have. The main division is 1 volt, and then the small divisions are going up by half. A dual scale meter has an upper and lower scale and allows the user to switch ranges as needed. Look at the following 2 meters. The one on the left reads exactly 0.4 volts, but the one on the right reads 0.65 volts to the nearest scale marker, or about 6.7 volts if we estimate between the scale markers. The smallest division is half a volt. On the following meter scale, the smallest scale division is 1/5 of 0.1 amperes, or 0.02 ampere. The reading at A is therefore 0.2 plus 4 small divisions, or 0.28 amperes. The reading of B is 0.4 plus 3.5 small divisions, or 0.47 amperes. On a non-uniform scale, spacing between the divisions changes at various places along the scale, and the number of units represented by each small division also changes. The following ohm meter scale is an example of a non-uniform scale. So it actually, you can see it's not consistent as it goes across. The following table gives the value of the subdivisions for each part of the ohm scale. On the ohm meter in figure A, the needle points to the second small division between 3 and 4. So this would be 2, 3, 4, 5. So the reading is 3 plus 2, or 3.4. So this was 2, this is 3, and then we went 2 past that, which is how we came up with this 0.2. And so it's going to be 2 times that because it's divided into tenths. I'm sorry, because it's divided into fifths. So 2 times 1/5 would give you 0.4. On this one, the needle points to only the small division between 30 and 40. So the reading would be 30 plus 5, and that's going to give us 35 ohms. Okay, so let's look at an example of this. You always want to start with your 100,000, and so you want to pick the smallest number if it's between two numbers. So it looks like it's between 5 and 6, so it would be 500,000. We're going to go clockwise, so always start with your 100,000, then you go to 10. It's between 1 and 2. Always pick the smaller number. On the 1,000s place, it looks like it's between 0 and 1. So we would pick 0, it's smaller. On the hundreds place, it's between 7 and 8. So you would pick the smaller of the two. Between 4 and 5. And in the ones place, we would pick, it's between the 0 and the 9. It looks like it's like right on the 9 though. So I think I'm going to go ahead and put 9 here. So the first blank represents the 100,000s place, the second blank the 10,000s, and then so on and so forth. So the needle on the 100,000 is between the 5 and the 6, and this goes over the example that we just worked. Okay, I was just making sure that was the same example, but it just goes over that exact same example. Many electric meters also contain circular dials representing the number of kilowatt hours consumed, as with water meters. The dial represents powers of 10. On the following electric meter, the 4 dials represent thousands, hundreds, tens, and ones digits of a 4-digit number of kilowatt hours. So to read the number of kilowatt hours, first draw 4 blanks representing the thousands, the hundreds place, the tens place, and the ones place. So next, read each dial as you did with the water meters, again choosing the smaller number whenever the number is between two numbers. So it's between 4 and 5, they picked 4. Between 8 and 9, we would pick 8. 5 and 6, we would pick 5. Between, and it looks like it's right on 3, so I'm going to go ahead and call that 3. Okay, so this goes through and just explains how to do that. Dial gauges, also known as dial indicators, are used to measure very small distances. They are useful to detect a difference in height along a flat surface. To center cylindrical stock, to monitor the depth of drilled holes, to determine if the edges of the rectangular surface are parallel, to perform many other precise measurements in machine tool technology, manufacturing, woodworking, designing, and automotive technology. So here's an example of metric dial gauges. Okay, metric dial gauges shown in figures C and D on the previous slide have two circular scales. Each small division on the larger scale represents 0.01 millimeters. Each number on the smaller scale indicates the number of complete revolutions made by the larger needle, and each revolution represents 1 millimeter. The larger needle rotates either clockwise or counterclockwise. A clockwise rotation is considered to be a positive deflection of the needle, indicating that the object being measured is larger than a standard or desired measurement. The counterclockwise rotation is considered to be a negative deflection of the needle, indicating that the object being measured is smaller than the standard or desired measurement. The arrows on the upper portion of the larger scale have been drawn to indicate in which direction the needle deflected. So if we want to read this dial gauge, it says first notice the arrow at the top of the dial points to the right, indicating a positive deflection. So when we look at this is saying we're going clockwise, so that's going to be a positive deflection. This means that the measurement will be positive number and that the larger dial will be read in a clockwise direction. Next, notice that the needle on the smaller scale is between the 4 and the 5. So down here, it's kind of hard to see, but this number is between 4 and 5. This indicates 4 complete revolutions of the larger needle, which represents 4 times 1 millimeter. So this scale has already gone around 4 times, 4 millimeters. Then, because the deflection is positive, we read the larger scale in a clockwise direction. The larger needle therefore reads 32, so we're at 32 times 0.01 or 0.32 millimeters. Finally, we add the 4 and the 32 together, and the resulting measurement is a positive 4.32 millimeters, or 4 32 of a millimeter. To read the dial gauge in figure D, first notice that the arrow at the top is pointed to the left. So this is a negative number. Notice that the needle on the smaller scale is between 1 and 2. So this indicates 1 complete revolution of the larger needle, giving us 1 millimeter. Remember, you go with the smaller number. Then, because a deflection is a negative, we read the scale in a counterclockwise direction. So this means that as we pass 50, the number 40 actually represents 60. This would be 70, and so on. So that's the needle on this dial is indicating 83. So by the time we've gone 50, 60, 70, 80, up to 3 millimeters. Finally, we add this to our 1 millimeter from the previous step, and we attach the minus sign. So minus 1.83 millimeters, or negative 1.83 millimeters. A U.S. customary dial gauge measures distances in inches. As with metric dial gauges, the smaller dial records the number of complete revolutions of the larger dial, with each revolution representing 0.1 inch or 1/10 of an inch. Each small division on the larger scale represents 1/10 of an inch or 1/1000th of an inch. Or, I'm sorry, this is 1/1000th of an inch, not 1/10 of an inch. As with the metric gauges, a clockwise rotation represents a positive deflection, and a counterclockwise is going to be a negative deflection. So if we want to read this gauge, this figure E, we want to notice the arrow at the top points to the right, indicating a positive deflection. So positive. The needle on the smaller dial is between 5 and 6, so we would go with 5 times 1.1. With a positive deflection, we need the larger scale in a clockwise, so we've got 50, but this would be 60, 70, 1, 2, so 72 times 0.001. And then we want to add those two things together, our 0.5 and our 0.072, which is going to give us a positive 0.572 inches. So if we want to, here's an example of a negative one, so we're going backwards this time. So remember, we've got 10, and then this one would be, it looks like it's really close to 17. And then on our smaller dial, we were between 2 and 3, so we would go with the 2 times 0.1, then 17 times 0.0, and we add those two numbers together, and then we add our negative at the very end. So that's the end of chapter 5. We're going to be moving on to chapter 6 next.